The next thing we're going to be talking about is even and odd functions. A function is said to be even if f of negative x is equal to f of x. That is, if the x's are negative, it's the same thing, the same function value as if the x's would have been positive. What that does is that makes it symmetric about the y-axis. Even means it's symmetric about the y-axis. Algebraically, we test that by plugging in a negative x and seeing if it matches with the original. A function is said to be odd if f of negative x is now equal to negative f of x. That is, if I plug in a negative for x, it looks like I flipped my equation upside down. So the whole thing is upside down. That makes it symmetric about the origin. So here we have two graphs that represent exactly that. The first graph is this one right here. And this one, I can tell right away it's not going to be symmetric about the y-axis. So this is not going to be an even function. However, if it's odd, it's symmetric about the origin. That means that on opposite sides, where you would have had xy, you would have negative xy. Another trick to find out if this is symmetric is to basically just turn upside down. Look at this graph. If I turn this graph upside down, does it look the same as the original? So I just rotate it. And look, I turned this upside down. Is that the same as what I started off with? That's one way to find out. Let's see. Is that the same? All I'm doing is going back and forth, flipping this thing upside down. And it looks exactly the same. Now leave it upside down just for fun. That tells me right away this is an odd function. If by turning the graph upside down it looks the same as the original, that means it did not move up, down, left, or right in the slightest. It has to look exactly the same. It means it's symmetric about the origin. Algebraically, we're going to find out how to prove that. All right, next one. On this next one, we have x squared plus 1. This one looks like we have a match on both sides of the equation. We have a match for where x comma y is the same as negative x comma y. We see that a lot with, well, even power functions. But one thing we also know is that if it is symmetric about the y-axis, I should be able to fold it or even flip it over the y-axis, and it looks exactly the same. Oh, that was not intended. There it is. Let's look at that again. Look at the graph. There it is the regular way. There it is flipped. You can see everything is written backwards, but the graph looks exactly the same. That's another way to see if something is symmetric about the y-axis. You should be able to fold it in half. There should be a match, an exact mirror on the other side of the y-axis. All right? So now let's take a look at this algebraically. We can check by graphing, but we do have an algebraic proof of odd and even. The first thing you need to do to see if something is even, general rule of thumb as well, is if you see even exponents, you should test for even. If you see odd exponents, you should test for odd. However, it doesn't instantly make it that way. So this one does not have an odd exponent. I should only test for even. And I do so because remember, it's even if f of x is equal to f of negative x. That's what makes it even. So let's see, f of x is up here. F of x is x squared minus 6. Let's see what happens if I try to plug in a negative for x. F of negative x, now this thing is going to read negative x, close parentheses, squared minus 6. That means that f of negative x is equal to negative squared is positive. And then the minus 6, there's nothing I can do with that. Look at f of negative x. Is that the same as f of x? And because it is, in this case, f of x is equal to f of negative x. This makes this function even. All right? Then, on the next one, we're going to test for odd. Again, I should not be testing for even. I can if I want to, but I can tell you right away, if it doesn't have an even exponent, it's very unlikely, and it probably won't have a situation where it's going to be an odd function because it has even exponents. Even exponents tend to eliminate negatives out of equations, which we want those to show up because remember the test for odd is that if I plug in a negative for x, it's the same thing as my whole equation going negative. So let's take a look. What happens when I plug in a negative for this equation? And actually this should read g of x, not f of x, which is fine. Just a label. But they're using g this time because we already did the f of x. But let's stay consistent. So g of negative x now is going to be equal to 2 and then negative x to the 5th power minus negative x to the 3rd power. So we're going to take this equation and simplify. So g of negative x is equal to a negative to the 5th power stays negative. So this becomes negative 2x to the 5th. A negative to the 3rd, same thing. So this becomes negative x to the 3rd. But a negative on the outside is going to turn that into a plus. All right, so g of negative x is equal to this. Let's compare this to negative g of x. Negative g of x means you take the whole equation and you're going to make it negative. That is, you put negative and then parentheses, which tells you, hey, distribute that negative. So negative g of x, negative of that is going to be negative 2x to the 5th. And then the negative distributes to the negative x cubed, which makes it positive. Look closely. How did these two quantities here compare? How does g of negative x compare to negative g of x? Negative 2x to the 5th plus x cubed, negative 2x to the 5th plus x cubed. They are equal. Those two things being equal makes this odd. Notice, negative g of x is the same as g of negative x. So by making everything opposite in sign, I ended up matching. If I substituted a negative in place of x, that tells me I'm dealing with an odd function. All right? So that brings us to the end of the section. You have a homework assignment. You may use the calculator for some of these. This is to be done on WebAssign. So please look on WebAssign for these, and if you have any questions, just have them ready next time.